Hey everyone, and welcome back to DevOps Corner. All right, if you're running workloads on AWS, you probably feel like you've got a handle on load balancers. I mean, they just distribute traffic, right? Simple. Well, today, we're going to tear that simple idea apart. We're going way beyond the basics to build a real, production-grade mental model of how they actually work, what happens when they're under pressure, and the critical, silent mistakes that can bring your entire application down, even when all your dashboards are green. So let's kick things off with a scene that's, well, it's probably going to feel a little too familiar for some of you. The alerts are screaming, users are flooding support tickets, your app is down. But you frantically pull up the EC2 dashboard and what? Every single one of your instances is passing its health checks. They're running perfectly. This is, without a doubt, one of the most frustrating types of outages because the problem is just not where you expect it to be.
The thing is, more often than not, the issue lies in the incredibly complex journey a user's request takes before it even gets close to your application code. The problem isn't the destination, it's the path. And to solve this mystery, we have to become detectives. We need to follow the evidence, and that means tracing the path of a single request from start to finish.
So at its core, an AWS Elastic Load Balancer is your app's traffic director. It gives you one single stable DNS name that your clients talk to, and then behind the scenes, it juggles all your backend servers. It's the gatekeeper for every connection. But as we're about to see, it's so much more than just a simple gate. To really get to the bottom of where things go wrong, we need to follow a single request from the moment it leaves the user's browser all the way until it hits one of our EC2 instances. This 5-step journey, this is the absolute foundation. So let's walk through each stage and we'll build out the architecture as we go. The whole process kicks off the second a user types in your domain name. Their computer fires off a DNS query to figure out what IP address that name points to. And here's the first key point. This IP address doesn't belong to one of your servers. It belongs to the load balancer itself. And you know what? The very first potential bottleneck in this entire chain happens right here with DNS, before your infrastructure even gets a chance to do anything.
Okay, once DNS has done its job, the user's browser shoots the HTTP request to that IP address. That request zips across the internet and arrives right at the front door of the massive AWS-managed load balancer fleet. This is the handoff point. This is where AWS takes over, and where the real magic and all the complexity truly begins.
And now we've arrived at the listener. This is where all the intelligence is. Seriously, think of the listener as the brain of the load balancer. It's a process that's constantly checking the protocol and port of incoming connections. If you're using an application load balancer, it can even terminate TLS/SSL for you, offloading all that heavy cryptographic work. But the most important job it has is to evaluate a set of rules that you've defined in a specific priority order to make a decision about where this one request should go next.
And this is what makes an application load balancer so powerful. It's not just blindly passing along traffic, it operates at layer 7. Which means it can actually look inside the HTTP request. You can set up rules based on the URL path, the hostname, custom HTTP headers, query strings, even the source IP of the user. This lets you do some incredibly sophisticated routing, which is pretty much essential for any modern microservices architecture.
So once a listener rule gets a match, it points to something called a target group. A target group is really just a logical bucket, a collection of your backend resources. And that target group has one absolutely critical job. It is constantly running health checks against all of its registered targets. So when it gets a request from the listener, it already knows which instances are healthy, and it forwards the request to just one of them.
So we've traced the flow. But, and this is a big but, the behavior of that flow completely changes depending on which type of load balancer you choose. Picking the right tool for the job isn't just some nice-to-have best practice. It's absolutely critical for performance, reliability, and even cost.
Now this is where things get really interesting, because this table shows a fundamental trade-off. You've got the application load balancer, the ALB, on one side. It's smart, right? It understands HTTP. But look at that last row. Your backend server only sees the load balancer's private IP. That means your app logs are going to be full of the LB's IP unless you go to the trouble of parsing the X-forwarded FAR header. Then you have the network load balancer, or NLB. It works at layer 4, so it's not as smart, but it is incredibly fast. And crucially, it preserves the client's source IP address. The original TCP connection is passed right through, so your app sees the real user's IP with zero extra work. For logging, security, or geolocation services, that can be a total game changer.
And when we say fast, let's put a number on it. The latency for a network load balancer is measured in microseconds. An application load balancer is usually in the low single-digit milliseconds. Now, for most websites, that difference is completely meaningless. You'll never notice it. But if you're building real-time applications like online gaming, financial trading platforms, or high-throughput IoT systems, where every millisecond is precious, the choice is pretty clear.
So the big question is, why is the NLB so much faster? Well, it's built on a totally different architecture called AWS Hyperplane. You can think of Hyperplane as this massive, distributed networking platform that powers a ton of AWS services under the hood, like VPC endpoints and network firewall. See, an ALB is basically a fleet of reverse proxy servers that have to scale up and down. An NLB running on Hyperplane doesn't have instances in that same way. It's this highly available service that can handle millions of requests per second with no pre-warming needed. This is a huge shift from the old classic load balancers where you had to open a support ticket to pre-warm them before a big traffic spike.
Okay, theory is great, but let's talk about what happens when things inevitably go wrong. A perfect diagram on a whiteboard doesn't mean anything if it can't handle the chaos of a real production environment. This is where health checks and failover behavior become your absolute first line of defense.
You configure your health checks inside the target group, and it's a really delicate balancing act. You've got the interval, which is how often the load balancer pings your instance. The timeout is how long it'll wait for a reply, and then the thresholds define how many failures in a row it takes to mark an instance as unhealthy, or how many successes it takes to bring it back into service. If you set these too aggressively, a server that's just a little slow might get yanked out of rotation for no reason. But if you're too slow, you'll just keep sending users to a dead server for way too long.
All right, let's put this to the test. Let's say a bad deployment goes out and an instance starts failing. Or maybe your Super Bowl ad just hit the airwaves and traffic is going through the roof. What does the load balancer actually do in that exact moment?
This right here is the beautiful synergy between elastic load balancing and auto-scaling groups. The very instant an instance fails its health checks, the ELB's target group marks it unhealthy and immediately stops sending it any new traffic. That's the super fast reactive part. At the same time, the auto-scaling group sees the unhealthy instance, terminates it, and starts spinning up a brand new healthy replacement. So the ELB handles the immediate traffic problem while the ASG handles the long-term capacity problem.
Okay, let's circle all the way back to our original mystery. The app is down, but the instances are healthy. This is the part that trips up even really experienced engineers. So let's put on our detective hats again and diagnose what could have happened by looking at the most common, painful production mistakes. Every single one of these can cause our exact outage scenario. So let's break them down. First, the classic, misconfigured health checks. Maybe your health check is just a simple TCP ping on port 80. Well, that tells you a web server process is running, but it tells you nothing about your actual application. What if your app can't connect to its database? It'll accept a TCP connection, but then serve a 500 error to every single user. The load balancer thinks the instance is healthy, but for your users, it's completely broken. A good health check hits an endpoint like /health that actually verifies its own dependencies before it returns a 200 OK. Next up, security groups, the silent killer. If your instance's security group doesn't have an inbound rule that specifically allows traffic from the load balancer's security group, AWS just drops the packets. The instance never even sees them. From the outside, it looks like a total outage, but the instance itself is just sitting there, perfectly healthy, wondering where all the traffic went. And finally, deploying in a single availability zone. Your load balancer has to be deployed across at least 2 AZs. If all your instances are in just one AZ and that zone has a problem, your load balancer has nowhere to send traffic. It'll mark every single target as unhealthy, and your service goes down.
So let's put this all together one last time. The user makes a DNS request, it resolves to the load balancer. The load balancer's listener gets the request, inspects it, and runs it against your rules. The winning rule points it to a target group, and that target group, using its real-time health check data, picks a healthy instance and makes the final connection. Every single request goes through this entire decision chain.
So what are the big takeaways here? First, remember that a request's path is a journey with lots of decision points. Second, choose the right tool for the job. ALB for smart HTTP routing, NLB for raw TCP UDP speed. Third, listener rules are where you put your business logic for how traffic should be managed. Fourth, your health checks have to check the real health of your application, not just the server. And finally, just remember our mystery from the beginning. 9 times out of 10, those unexplained outages, they're not some deep, complex bug. They trace right back to a simple, overlooked mistake in one of the steps we just covered.
And that leaves us with a final thought to chew on. We've mastered the flow for a simple app.
But what if your service relies on 3 other downstream microservices to work? Should its /health endpoint check the status of those dependencies too? What are the risks of that? And how could that design lead to cascading failures? Thinking through these complex, messy, real-world problems, that's the next step to truly mastering your architecture.
Thanks so much for watching. If you found this useful, do me a favor and hit that like button and share this with your team. And of course, subscribe to DevOps Corner for more explainers just like this one. See you in the next one.